In this video, we're going to review when limits exist versus when they do not exist. So we've talked about this before, when limits exist and when limits do not exist, but we're going to state our results with more precision than we've done before. Okay, so the question I want to begin with is, what does the graph of f, my function, look like when the limit as x approaches a of f of x exists? So what would that look like? Okay, so there are three possible ways my graph could look like, and they're all kind of close to each other in appearance. So I'm going to draw three coordinate axes here, so my xy axes. Okay, on each of these, let's say this is where A is, so A is somewhere over here. So in the first scenario, this is maybe the simplest one, is what if my graph is just continuous? There's no holes, no asymptotes, just at A. The value of the function is going to be some number L. That's the y value. Okay. So that limit exists. The limit as x approaches a in this graph will exist. And I'll recap why after I've drawn each of these pictures. Okay, but in the next picture, let's draw a similar looking graph. Oops, a similar looking graph. Well, that's actually, yeah, let's put this in blue actually. A similar looking graph. But when I get to A, let's put a hole there. And then the graph just keeps going. And let's say the y value of that hole is L again. Even though this graph is not continuous at A, it's discontinuous at A, the limit will still exist. Because the left-handed limit and the right-handed limit are the same. They both equal L. When we talk about limits, we don't care what's happening at that exact point. We just care about what's happening close to that point. So it's totally fine for there to be a hole there. And that's actually gonna motivate my last example. So a similar picture again. Let's put a hole there, keep on going. But what if there's actually a point at x equals a somewhere, like maybe it's up above here somewhere. But as long as the y value at that hole, so if I say the y value at the hole is L, this limit's still gonna exist because the limit from the left and the limit from the right are both gonna be equal to L. That's what the y values get really, really close to. So in each of these graphs, let's just recap, in each graph, the limit, well, let's write that a little bit better. Each graph, the limit as x approaches a of f of x equals L. And the fact that the limit is a finite number is what tells us that the limit exists. So it being this finite number means the limit exists. Okay, but why does the limit actually equal L in each of these? Well, the limit equals L since the left and the right hand limits both equal the finite number L in each of these graphs. Again, it doesn't matter what happens exactly at x equals a, because when we talk about a limit, x is getting super, super close to a, but it's not allowed to actually equal a. That's why it's fine for there to be a hole there. Okay, but the fact that the left and the right hand limits are both L, the y values are getting close to L from either side in each of these pictures, is why the limit exists. All right, so next let's review what a graph looks like when the limit doesn't exist. All right, let me scroll up a little bit actually. So the question that I want to ask is, what does the graph of f look like when the limit as x approaches a of f of x DNE does not exist? So in section 3.1, we had actually drawn some pictures of what this could look like. And I've actually just copied down those exact graphs from before. So we've seen each of these pictures before, which is why I've just copied them down instead of just drawing them again. Okay. And we stated that the limits, the corresponding limits in each of these graphs. So the first one is x gets close to 1, and the second graph as x gets close to -2, and in the third graph as x gets close to 0. All of these were DNE. All of them didn't exist. Okay, but let's just recap the reasons now that we have this framework of the left hand and the right hand limits, to be a little bit more precise. So for this first graph, this graph on the left, what's the reason that the limit doesn't exist? So the reason that this limit doesn't exist is the one-sided limits are different. We need two things for a limit to exist. The one-sided limits have to be the same, and they have to be finite. If either one of those it does not hold, then the overall limit, in this case the limit as x approaches 1, does not exist. So in this picture, the one-sided limits are different, and that's what makes this limit not exist. The two-sided limit, or this overall limit. Okay, so for the second graph, where I have this vertical asymptote and my graph is getting really, really large on either side of the vertical asymptote, I want to review a little bit of notation before we talk about the reason why the limit does not exist. So in this graph, we run into a scenario, but I want to state a more general version. So if the limit is infinity or negative infinity, so if the y values are either going to infinity, in this case it's a two-sided limit, so from both sides, or if they're approaching negative infinity from both sides, then the convention is that we specify that. We specify which one rather than write DNE. So if something like this was a test question, and it asked, oh, here's a graph, the limit, what's the limit as x approaches negative 2 of f of x? And we wrote DNE. We wouldn't get full credit for that. Although it's right that it is DNE, it's just not specific enough. In this case, we would need to write the limit as x approaches negative 2 of f of x equals positive infinity. That has the right level of specificity. When we write infinity, that implies it's DNE, because it's not a finite number, but it's also being more specific. It's telling us more information about what the graph looks like. It's saying the y values are getting huge as x gets close to this number. Okay, so what's the reason why this falls into the DNE category? The reason why is, I'm going to frame it again into this context of one-sided limits. The one-sided limits in this problem are the same, so that's good, but they're infinite. They need to be finite. The one-sided limits are, let's just erase that, are infinite. And that's bad. Okay, so in the first one, the one-sided limits were different, and that was bad for us. In the second one, the one-sided limits were infinite, and that was bad for us. So this third picture we had seen before as well. It's this sine of 1 over x graph that oscillates up and down like sine does, but as x gets really close to 0, where this function is undefined, because you get 1 over 0 inside the sine, and dividing by 0 is always undefined, our oscillation gets quicker and quicker and quicker. In fact, it gets infinitely and infinitely quicker. So the reason why this limit doesn't exist is, just in terms of the one-sided limits again, the one-sided limits in this graph do not exist. Since f of x, our function, hits every value in the interval from -1 to 1, so between -1 and 1, including them, infinitely often, so infinitely often, as x approaches 0. So as a result of that, f of x, which means my y values, f of x approaches infinitely many values, because it approaches everything between -1 and +1 an infinite number of times. Okay, but for a limit to exist, f of x is supposed to approach just one value. So in terms of our goals for this section, now we've reviewed when a limit exists and when it does not exist, but a little bit more closely under the framework of the left-hand limit and the right-hand limits needing to be the same and needing to both be finite. In the next video, we'll introduce what are called the limit laws.